come in. All right, I'm ready to
All right, ladies and gentlemen, recording has started.
What about tomorrow?
Yeah.
For a review?
Well, let's see how far we get today. So, first, right now we are on track for test on Monday. I did build in another day in there in case we didn't get all the stuff done today that we were supposed to get to. We can kind of roll it over in Friday a little bit. So we'll see how far we get today, what we get through, what we don't get through, and we'll see if we have to adjust that. But right now, we're on track for test Monday. Objective sheet is posted, so if you haven't looked at that yet.
Yeah, it's in.
A lot of stuff is in. I mean, we've talked about it a lot. So.
But that's good.
All right. Yesterday, we got into the life cycle of the star. And we said that star, regardless of what kind of a star it is, it all sort of starts like this. Right? Star starts as a nebula, a big cloud of gas and stuff. And then gravity starts pulling it together, and as gravity starts pulling it together, it goes faster, and as it goes faster, it gets hotter, and blah, 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 blah. And eventually it becomes a star if there is a requirement if we're going to make a star. So we had to strike a balance between two things. What are the balance we have to strike there? Lauren, you want to go ahead?
Isn't it the inward pull of gravity and propulsion of the heat?
How about the expansion, right? So yeah, we have to strike a balance between that inward pull of gravity and the outward expansion caused by the heat of fusion. And if we do that, then we make ourselves a star. Right?
Is there a time that it just stays in like the proto-star thing where like it just never balances?
Yep, like Jupiter.
Oh,
Okay.
so it's just
Jupiter is a big ball of gas, but it didn't quite have enough gravity to get that heat hot enough to make fusion
will it
go in.
ever, or
No.
will it no?
At least not now. That led us to the HR diagram, right? An HR diagram is a graph of temperature on the x-axis, brightness on the y-axis, which said that brightness is a measure of what? What determines the absolute brightness of a star?
Mass.
What is the absolute brightness actually measuring? How much energy is being given off, right? And that comes down to a lot of things, color, size, and stuff like that. We said that that big stripe down the middle we refer to as the main sequence, and that depending on the mass of the star, that'll show you where you end up on the main sequence. And as long as the inward pull of gravity and the outward push from the expansion to the heat of fusion is good, it stays on that main sequence. But things start changing when what happens? When the star starts running out of what? Hydrogen to fuse together. Okay? So we talked about that the first thing that happens is if the fusion slows down, the outward push decreases, and what initially happens? Before it actually gets a little bit smaller first, but then that kicks fusion back up, and then with things higher than hydrogen, and then it gets really big. How big? Well, this morning I was looking for some stuff, and I found this amazing resource out there. It's called Your Textbook. Okay?
Please read every.
I know. We probably should, because it has a lot of really good pictures in it, like this. So, anyway, here is a picture that shows you how big our sun is going to get when it becomes a red giant. This yellow dot in the middle is how big the sun currently is. Okay? Yeah. So, Chris, go ahead.
So is the sun really gonna blow over? Because
Our sun is not.
someone over there, I forget who, said it wasn't going to.
No, our sun is not going to.
It's not going to.
It doesn't have enough mass.
So what's this presentation?
Well, this is not a blowing up. All right. This is not an expansion, not an explosion. Okay. So Chris, yeah, it's not like an explosion. It just keeps getting bigger and bigger and bigger and bigger and bigger. Okay. And it gets this much bigger. Okay. Where Mercury, Venus, Earth, maybe Mars, depending on who you believe, all just sort of get gobbled up by the sun. Are we going to get burnt to death? No, we're going to be long gone by then. So, most likely. I mean, you and I, obviously, but
No,
humans as we know them probably won't exist at that point in time. Okay? If you look at the time frame, our sun is about 5 billion years old, and this is not going to happen for another 5 billion years. So our sun's about halfway through its lifetime. Yeah, pretty much. So,
It's in its midlife crisis.
kind of. So.
Yeah.
Lauren, go ahead.
So how long does it take when it's supposed to be the right guy? How long does that take?
So, Lauren, another good resource from your book is the text that actually appears in your book. So, I know, it's crazy. So, kind of hard to read, but the red giant phase lasts about 100 million years. Okay, which is a long time. But if you consider that the star itself is no. So the star itself is 10 billion years old. Okay? The red giant phase lasts this long. Okay? Which is a long time, but not anywhere close. I mean, it's a very small portion of the star's lifetime, right? So if we're talking about this is happening at the very end of its lifetime, right? And it all happens relatively quickly, right? Not over a matter of a couple of days, but relatively quickly this all happens. Okay?
How long does it take to like transition?
Oh, I don't know exactly. So I think this 100 million, the blue one, is how long it takes to become a red giant, how long it stays a red giant, and that kind of stuff. So, anything go ahead.
Where did they get the number?
You can look. Okay, so this number, the 10 billion, you can kind of look at. All right, how much hydrogen and how much helium exists in the sun right now, and we can figure that out by looking at the light that's given off and the spectra of the light, stuff like that. And so we see that there's basically a 50-50 ratio of hydrogen to helium, which means we're about halfway through. So if you calculate the mass of that sun, right, and say, okay, half of it's hydrogen, half of it's helium, you can sort of project out how long did it take us to get there, and then how long will it take us to get to the end.
So, like, if the sun was like a red giant, would light be darker?
It would be red, right? But the one thing being, right, we talked about the idea, like, absolute brightness is how much energy is being given off, but apparent brightness is how it looks to us here. The sun has the highest apparent brightness of anything in the sky. Not because it's the brightest thing out there, but because why? We're so close to it, right? Even if the sun would expand to the size of just the orbit of Mercury, right? It would still be much, much closer to us then. So even if it's cooling down and it's not as hot, we would still get more of that energy because it's closer. Does that make sense? Right, so you have to factor in that sort of thing. Would it look red? Yeah, it'd probably look a little reddish, right? Like, you know, the sun itself would look red, but we'd still have other colors. All those colors still exist in sunlight, even though it's quote unquote yellow. And we'll talk more about that like next. We talk about spectrum and stuff like that.
So it just gets to the Mercury, but it's still like the same apparent.
Actually, probably a bigger apparent brightness, even though it's cooled down. These aren't on the HR diagram. Those aren't necessarily direct relationships between temperature and brightness. All right, we good with that? And then after that, right, we said our sun just kind of fizzles out, right? That it goes down this path, right? That it gets big, and then eventually what's going to stop altogether? Fusion's going to stop altogether, and then it just kind of goes. And the stuff that, you know, was around in the planetary nebula, that is the stuff that used to be part of the star, but just sort of dissipates because the fusion stops, and the gravity is spread out over a much bigger region, so some of that planetary nebula stuff may be attracted to other things or whatever. Okay, go ahead.
Is a planet? Where does a planet come from?
A planet comes kind of from the same thing as a star, where we have a bunch of dust and rocks and things like that pull themselves together. But I mean, obviously, it causes the temperature to increase. If you look at the core of the Earth, right, it's a lot warmer than the surface, but nowhere near hot enough to do fusion. So it's kind of the same process, just with the small mass doesn't get you to that temperature where fusion starts. All right. What we said yesterday, did we get to any of the good stuff yesterday? Big stuff?
Everything was correct.
So let's go here. So we talked about that stars that are similar to our sun and smaller will go that top route, all right, and just sort of fizzle out. Okay. As a matter of fact, that awesome resource I referred you to earlier, your textbook, says that things that are the size of our sun, and then up to things that are about 40% bigger than our sun. So 1.4 solar masses, how they refer to it, right? Things that are, a little bit bigger than our sun will ultimately go that route. But stars that are bigger than that, 50 to however many times bigger than our sun, will go the bottom route. It still starts off as the red giant, except now it's a red supergiant because it was bigger to begin with, and so now it's obviously bigger than. Okay. Fusion slows down, gravity pulls it in, pressure, temperature increase, that kicks fusion back up. We start making heavier elements all the way up to iron, right? And that causes the expansion. But just like in the stars on the top row, what's eventually going to happen inside of this star? Fusion's going to stop. And if fusion stops, what takes over? Gravity. Gravity crunches all those things down, right? But do all those parts of a star like being crunched down together? No, they don't, right? So then we have our big explosion of the supernova. Okay?
Wait, so what's different from this from the other route when it's just like that?
Yeah. So
Like the planetary nebula.
Allison, with the planetary nebula, right? At that point, the star the size of our sun has spread out so much that gravity really can't kind of pull it back together anymore. It's been spread out so big.
Oh, and this one is spread out.
Well, it's spread out big, but it has so much more mass because it's a much bigger star that the gravity is still strong enough to pull it all back together. Does that make sense? Okay. It has to do with how much mass is there and how much gravity is there. Can gravity sort of keep it all together longer or not? And that's really what determines what happens.
This one's done.
This one keeps it together a little bit longer.
Because it has a bigger mass.
Right. So that means it has more gravity. Okay. Same question.
But it says this results in when fusion stops, the huge gravity, like huge amount of gravity.
Right, yeah, that's a lot of gravity, yes. That's good. And in the supernova, the conditions, the temperatures, and the pressures are big enough that now we can put fusion together, or we can fuse together elements to make things that are higher than iron. Now, do supernova happen all the time? No, they don't. So if you look at the percentage of elements that are bigger than iron, right? If you look at how much of the universe is made of uranium or lead or gold, it's not all that much because the conditions required to make those things don't show up very often, right? After the supernova, one of two things can happen. The supernova. So, quote, smaller big stars, all right? People, actors that that aren't Brad Pitt, I'm trying to think who would be, whatever.
Ryan Gosling.
Maybe
No.
Ryan Gosling.
No, he's Robert Downey
No,
Jr.
he's pretty popular.
Robert Downey Jr. is pretty
I love him.
mega. I mean,
Jude Law.
Jeremy Lin.
But he's popular, so.
Anyway,
Corbin
so
He was my favorite person.
the core of those quote-unquote smaller big stars turns into a neutron star. a neutron star, still warm, right? That's why it's still a star, it's still giving off energy, right? But it has so much gravity and so much pressure inside of it that it can actually take protons and electrons and fuse them together into neutrons. So you might be thinking, well, protons and electrons stick together on their own if they're oppositely charged. Yes, that's true, but there's a difference between two things sticking together and smashing them together so hard that they become the same object. And that's what neutron stars can do. The second one, smash protons and electrons together to give you neutrons, right?
They're both.
Because protons have a positive charge, electrons have a negative charge. If you smash them together into the same object, you'll get something that
Don't you need a lot of energy?
a lot of gravity and a lot of energy, yes. But that's what neutron stars have. Okay. Yeah, they're small because the force that is required there comes from the fact that we've packed a whole bunch of mass in a very small space. The gravity is very strong inside of there.
Like Earth small?
Probably Earth small, but you're talking about like a star smashed into the space of Earth. I don't know for sure though. That's good.
What's bigger, proton or electron?
Proton's way bigger than an electron, but they carry the same charge.
So it transferring might be like a little more positive.
Right. Yeah, they carry exactly the same amount of charge, even though one's much bigger than the other one. Awesome. Good.
So, they all go into like supernova, but like the smaller of the bigger ones go into neutron stars.
Right.
And then we're gonna learn that the biggest ones go into a black hole.
Is that like how neutrons are formed?
Pretty much, yeah. So, because like at the beginning, really, neutrons are kind of unnatural. Like, why would you make a neutron? But that's kind of where they come from. And then, they sort of get dissipated. I'm sure neutrons get made in this supernova as well, but they like end up outward and blah blah blah. But your biggest stars, right? Your biggest mass stars, they don't go that route. Right? They go the other route, right? These are your Brad Pitts, your George Clooney's, your Angelina Jolie's,
Jude Law, Robert Downey Jr.
George.
What? Are you kidding me? That's an insult. Are you?
Are you really going to compare Jude Law to Brad Pitt?
Wait,
No.
Jude Law's so much better than Brad Pitt.
Who's
So
Jude Law?
much better.
There you go. Good setting. Good setting. Good setting. And set. Eight. So, Nick didn't even know that Jude Law was a man. I guess the other two are seeing you.
Alex is a funny
I guess that ends that debate as who's the bigger star, right? You got any question what sex Brad Pitt is? Or? Okay, good. All right. So.
Picture of Jude Law.
No, not right now. Because Jude Law is lowly neutron star.
No, he's not. He's a super.
All right. So.
That is. Okay, he's English. You're American.
That's racist.
I mean, like the Beatles song. Yeah,
Dr. Watson from Sherlock Holmes: The Game of Shadows.
yeah, but,
I know.
But what I'm saying is.
Oh, that's Jude Law.
Okay.
But what I'm saying is.
No, I
Definitely like
Oh
a
my
baby.
God! No.
But what I'm saying though, in terms of this discussion, he's Watson. Robert Downey Jr. Right?
I looked at both, but yeah.
All right.
Is this what the other students?
No, this isn't the other question. This is the other question. No, this wasn't their debate.
Gosh, you guys don't know what you're talking about.
No.
When I get married to him.
The question, the debate is not whether he's hot or not. The debate is whether he's a neutron star or a black hole.
Well, first, you have the HR guy. And it's really funny because I know all the stars they go in a black hole.
Robert Downey Jr.
Oh my God, I know him.
Alright.
Too long, Robert Downey Jr.
So wait,
fine.
let's be serious, okay? Lindsay Lohan is definitely on the route of our son, okay?
Yeah.
Let's be serious.
She's so good.
Yeah, after Meet Girls, it's pretty pretty much been all downhill.
Yeah.
So,
Or no,
What about
Kirby.
exactly. Kirby fully loaded is like the equivalent of Kirby time. Like she tried to get big and then it just went. And you know what this was? Like, if we go Miley Cyrus, LOL is like her going from a white dwarf to a black dwarf, alright?
What is that?
Exactly. It just came out last week. It's a movie with Miley Cyrus in it. Nobody knows about it.
How do you know?
Alright.
That all recorded.
I re-got it. So it shows up. And it was basically like, hey, this new movie stinks. So. Alright. Alright. Order. Order. I mean, I know who you are. Alright. Order. So.
Just sit back in the box. Yeah.
So. Your biggest of the big stars end up as a black hole. The black hole is the core of the star, just like the neutron star is, except there is so much mass condensed down into so small of a space that the gravity is so strong that not anything, sorry, bad English, there is nothing that can escape the gravity. Not even light. Okay.
What about wormholes?
Yeah, it's all very speculative.
Where does it go?
Okay. It's a good question. Very good.
How do we know those exist?
Okay.
Tell me
Right.
stuff
You can't really see it, right?
So like,
But
if we can't see it, then if we got too close, wouldn't we just fall in?
yeah,
Where do you go?
you have a warning, right? Because there's this big black spot in space that things keep heading towards, and then all of a sudden they disappear. So it's like, must be something there.
Where do you
You know?
go?
I just asked that.
It's a really retarded.
So now the problem is, okay.
Maybe we have to throw it out before
No,
they cut it.
see, the problem is you can't do that because even if you go in, no, it's not even that. Even if you go in, you can't send like a message or a signal out because nothing can get out of it.
Is there like any type of way that we can get out?
Nope. At least not that we know of.
How do you
Maybe
how
there's
do
a
you
ladder.
Hold on.
What if we like found out that we can go into
Really
a black
tall,
hole and just pop out of it?
It's like,
No, good.
Oh,
Nothing that requires.
well, if we brought a video camera, wouldn't it just get condensed and wouldn't it be
So there is, as far as what we see when things are heading towards the black hole, what happens is, so here on Earth, we talked about that the amount of gravity that exists between objects depends on their mass, and then it depends on the distance between them. Okay. Here, if we take whatever this stapler and move it from this desk to here, is it farther away from the center of the Earth? Yes. I mean, it is, but is it any significant distance farther away?
No.
So that really doesn't change the amount of gravity this stapler feels from here to here. However, a black hole's gravity is so strong that the distance, let's say, of you, if you're heading towards a black hole, the distance between your belly button and your back is a significant distance, so that there's actually more gravity acting on the front of you than the back of you. If there's more gravity acting on the front of you than the back of you, what starts happening, Nick? The front will start going faster than the back. It starts shutting you out. And I'm not joking with you.
We wouldn't be able to see anything also.
Right, that's the problem, is that we see this as it's heading towards it, but then all of a sudden it stops because we can't see anything else. Okay? We refer to that process, I'm not
Spaghettification.
spaghettification.
how would you know?
So, great question.
I was just to say, black holes, I was just saying, like, don't switch out, so they
Yeah.
would know it's
Well, I mean, wouldn't the windows on
Well,
like,
then, I mean, but then, like, your heart, like, you know, the front of your heart would start to stretch
Stop.
going into the back of your heart.
Okay, nobody's going into a black hole.
Yeah, nobody's going into a black hole, so it's alright.
Isn't a black hole supposed to fall?
It's like greater mass, greater gravitational pull.
Right, and that, because the mass is so large, that a small change in distance will make a big change in the force of gravity that it experiences even from the, you know, within the same object. Okay? Also good.
Will we ever find out where you go, like, in a black hole?
I don't know. I mean,
Probably not.
no.
What a wild way to
Anything
find
that we
out.
know of?
Things, yeah, we can see things going into a black hole,
Have we
but
thrown anything into a black hole?
no, we're not close
You
enough.
have to make like
We're not, we're not,
you have
we're
to
not
make like a solid like scale of anti-gravity chain.
Anthony,
Are black holes flat or three-dimensional?
You don't know.
not really sure.
I'm gonna guess the flat.
It's good.
No, what about warm?
Wait, we're not gonna go.
Let's not go there. Because I don't have an answer for you.
I'm.
So,
Let's Google it. What makes a pulsar?
I will Google it.
what?
What makes a
Look
pulsar?
at video.
A pulsar? A pulsar is, from what I understand it, it's like a star that is like circling. So, and it's shooting out energy as it circles. So it's kind of like a lighthouse where you see like the energy and then you see the light and you see it. So it looks like it's pulsing because it's spinning. That's what I understand, like a pulsar. All right, so are we good with this idea of black holes?
Jude Law? Yeah.
How much money would it cost for any like student talking to high school?
What?
Where's the closest? Do they know where the closest one is?
Yeah, probably, but it's too far away. So, yeah.
So like, are we?
Yeah.
Are you kind of like everyday like slightly or sun gravity?
We're too far away for that. All right. So,
Do you believe in crop circles and shit like that?
do I believe that you can make a circle out of a bunch of crops? Yes.
Do you think that it was like human, like?
I didn't say that. You asked me if I believe in
Well,
crops.
no, I mean like you know how there's random ones, aliens.
I
Do you believe in life on other planets?
I believe.
There you
Yes,
go.
like, it's not even.
I believe that the universe is so large, and there's so many stars.
We will never
That-
be able to.
We'll never be able to see it, but my personal feeling is if we think that in this entire universe that this Earth is the only place that has the conditions that are right for life, that'd be awfully arrogant of us. So
I think there's other
we're
places.
arrogant people. We are arrogant people, but you
I
know.
wonder if they have like 3 heads and like.
All right.
No, they probably look like us.
What if you
Yeah,
have
we can
opposite?
live on another
What if you're
planet.
like, oh, so that
What?
you'd be like, what?
So now, Miriam, just because the conditions might be right on another planet, does that mean life will evolve on that planet like life evolved here? That I don't know. That's true.
The conditions are identical to ours, I think.
Well, I mean, the possibility exists, but that doesn't necessarily mean that everything will go exactly the same way it went here. You know what I'm
I
saying?
mean, if you have the same atmosphere and the same climate, like everything, like Earth is just like property,
So,
then I think it would have.
so Nick, to argue that point, okay?
Doppler effect.
To argue that point, right? You and Piers sit right next to each other in class every day,
Yeah.
right? The same exact things are said, the same stuff goes up on the board, right?
Yeah.
But do you end up with the same test grade?
No, spot.
Well, I mean, but see, that's what I'm saying, is that just because the conditions are the same, doesn't mean that the outcome will necessarily be the same. And there's other factors there. Alright.
It's not the same.
We're different people. I'm saying like
But they're planets. You're wrong. Yes, you are.
He's standing on the side of the road.
I've heard of the Doppler effect.
Yeah,
All right.
on the news.
So let's talk about here, this discussion starts.
Big Bang.
How did it all begin? How do we think it might end? What
Yeah,
evidence do we
I
have?
like it.
So, the start of building a case for what we think happened at the beginning of the universe starts with the Doppler effect. Okay? The Doppler effect says that the motion of an object will cause a change in the perceived wavelength of energy that is being given off. Okay? What does that mean to you? The biggest Doppler effect that you guys that experience most often is that one that goes with sound. Okay? The sound of something changes as it moves towards you and then it moves away from you. Sirens are a good example. If you listen to a siren on the way as it's moving towards you versus as it's moving away from you, you'll notice there is a change in the sound of it. It doesn't sound the same. Okay? Or if you've ever watched racing on television, where they have a camera right by the side of the track, as those cars come towards you, they sound a little different than they do when they go away from you. Okay? It causes a change in the perceived wavelength. Okay? We'll talk more about that when we talk about waves in the next section. But as the source moves towards us, the frequency increases and the wavelength decreases. There is a perceived increase in frequency. Any guess what the other one's going to say? Okay. As it moves away from you, the frequency decreases and the wavelength increases. In sound, that shows up to you as a higher pitched sound versus a lower pitched sound.
It doesn't.
Not really.
I did it like school, Alex. Yeah, I know. So it just seems my measure.
I squeak like when it's like moving towards you.
Because what happens?
Well, I'm saying wavelength.
Okay, wavelength is the distance between these orange lines. Okay. So as they are coming towards you, they start piling up on each other, and so the distance between them gets short.
Oh, and then when you go, like it's further.
Right,
further.
right. It's stationary.
Oh, that's weird.
All right. Like I said, your experience with the Doppler effect is mostly limited to sound. Okay, but it happens with all kinds of waves, and it happens with light. Okay. Scientists start looking at these waves from distant stars, knowing that stars are made up of hydrogen. So we take a look at the waves that are emitted by hydrogen gas here on Earth, and then we look at these waves that are emitted by stars that are far away, and we find out that these waves from outer space are experiencing something that we call a red shift, most of them. Okay? There's a difference between a red shift and a blue shift. Red shift is up here. Okay. Things that are moving away from us, if we look at stars and galaxies and stuff that are moving away from us, they have sort of a reddish tint to them because we're seeing a decrease in the wavelength. Sorry, increase in wavelength, decrease in frequency. Go ahead. Say again. Because red light has a longer wavelength than blue light. Red is the color of light that has the longest wavelength. Violet is the color of wavelength or light that has the shortest wavelength. So when we say it's a red shift, we're looking at those things and we're seeing, oh, these are closer to red light than they really should be if they're made out of hydrogen and helium. Does that make sense? Sophisticated equipment that you don't have. Alright? But I don't. Because it's expensive, you have no real reason to need it. Yeah. It doesn't affect your everyday day-to-day life. Not like Hubble. Okay, so Caroline, go ahead. Talk about Hubble in a second.
I thought that the colors were referenced like the temperature. So like, what is the?
They can be. So with that, Caroline, if we're looking at a star that's a certain temperature, we think it's a certain temperature because it has a certain mass and stuff like that. When we look at that light, and it's really like more reddish than it should be.
Okay.
Like it really should be like blue, but it's more like drifting more towards yellow, based on what we believe its mass to be, and then where it is in its life cycle. We're like, okay, this really should be a blue star, but it's more like whitish yellow instead of blue, because of the whole red shift idea that it's shifting those colors downward. Okay. Anthony, go ahead.
So, like, when something emits, like, waves, it would be blue and then turns to red?
Yeah, kind of, although it's not necessarily it's blue turning to red. It'd be more like it's orange and turning to red. Like, it's not as dramatic as a shift as that. blue and red have very different wavelengths. But if you look at like Roy G. Biv, right, you know, orange to red isn't that big of a shift. So, but there is a shift towards the red side of the spectrum. Okay. So we start seeing this, and a guy named Hubble, who you may have heard of before, not for his law, but for his telescope, which isn't his telescope, it was named after him. Are we familiar with the Hubble telescope? What? No, that's the Hubble telescope is the one that's in space that is out in orbit. So there are a couple of huge telescopes in Hawaii. So 1929, like the mirror is like bigger than this room.
It just like goes in the ground.
In 1929, American scientist Edwin Hubble notices this redshift and puts out there the idea that if we're seeing light that is shifting towards the red, that means that the source of that light must be moving away from us. Just like if we hear a fire truck getting lower pitched, it's moving away from us. So Hubble says these galaxies must be moving away from us as well. And so,
Where did he live?
I don't know.
Oh, American.
He's American, but yeah.
American.
So he realizes that all of these stars and all of these galaxies are moving away from us, and that the farther the galaxy is, the faster it's moving away from us. And this all comes from experimental data, looking at the spectrum of light that's getting to us from these stars and blah, 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 blah. Okay? And that's Hubble's law. That's the next part of this story. Right? Oh, pet. No, we're not pets. All right. We will continue with this.
This is like constantly. Why isn't it like removed